Hello everyone, my name is Daniel Lenton and I'm the founder at Unify AI, where we're on a mission to unify all machine learning frameworks. Really nice to see you all today, and yeah, hope you're having a good conference so far. So today I'm going to be talking about how with Ivy you can accelerate your AI with one line of code. So first of all, I'll go over Ivy in a nutshell. So I'll be talking about a high-level overview of exactly what Ivy can do. Then I'll go into the design, specifically what is Ivy, how is it designed, and what role does it play. I'll then go over Ivy as a framework, so how to write framework-agnostic future-proof code. I'll then go over Ivy as a transpiler, and then how we can use this to bring code from other frameworks into your favorite framework. And then I'll be talking a bit about our team and yeah, kind of how you can apply and so on. Okay, so first of all, Ivy in a nutshell. So just to give a high level, obviously we all know that machine learning has advanced tremendously over the past few years, but unfortunately this has occurred firstly across many different AI frameworks. So these are the tools where you actually build your models and create new things. There's a load of different frameworks, all good in their own right, but none of these are compatible at all. We then have a layer below, which is the compiler infrastructure. So this is basically the stuff that's used to convert the models that are built using the frameworks, to convert these down into efficient representations that can then be deployed. And again, we have a lot of these incompatible tools used for compiling the code. And then we have a myriad of incompatible hardware as well at the bottom. And the hardware is basically what runs the ones and zeros, actually kind of does the computing under the hood, underneath all of this. So it takes those efficient representations and it crunches the numbers for us underneath. So we have these various fragmented levels, and this causes lots of problems for all kinds of people in AI. And one example of this is builders. So if you're building your AI model, at the moment you are entirely limited to the tools and models and libraries that are linked to your particular framework. So you don't have the ability to, for example, take a model from JAX and bring it into your TensorFlow training pipeline, for example, at all. It just won't work, and then what you need to do is to painstakingly re-implement this model line by line and so on. And this is really a case where the devil is very much in the detail, and it's very easy to make mistakes, and this is not good for rapid prototyping during the experimentation phase. And even if you get this working, let's say you get this working and then it goes, and you can imagine then trying to deploy this, you still have to deal with this fragmented stack. So let's say you've been using TensorFlow in your project, you somehow need to get it to go from this TensorFlow representation down through some compiler infrastructure, and then finally down to the hardware for actually crunching the computation. But what you'll notice about this stack is that it is sparsely interconnected. It is not, not everything connects to everything else. And what this means is that then when you try to ship out your product to lots of end users, and you need to try to find some way down this stack, you end up having these sparsely interconnected wires, and you can't leverage everything. So you're using TensorFlow in this case right at the top. It connects to some of the compiler infrastructure, and that might be pretty good, but it might not be the best. And each of these again connect to some of the hardware, which might be pretty good, but maybe not the best. So you take this sparse route down through a subset of the stack, and you then don't know what you're missing. There are cutting edge technologies that are not connected to what you're using, and you therefore don't leverage all of the optimization capabilities that would be possible. And this then leads to end users that potentially have to wait longer for their jobs and their API requests to complete. This can lead to them being frustrated. It also leads to anybody that's deploying models on scale to be spending a lot more money than they need to be spending. So we've talked about the bottom side of the stack. Now let's go one level up. There are actually lots of great frameworks and libraries and tools that have built on top of this stack. Really, really useful. But the problem here again is that they are then bogged down trying to make sure that they stay connected to all of the frameworks below. And this means that a lot of really valuable developer time is spent just trying to keep up with this infrastructure and not really making the tool as good as it can be. And again, so really just kind of, I mean, it would be an exaggeration to say that this ongoing frustration causes the entire stack to spontaneously explode, but it's certainly not sustainable, and it would help everybody if things were just more interoperable and more seamlessly integrated. So with Ivy, we connect the dots, and we are working to connect all of the hardware, all of the frameworks, all of the infrastructure with a seamless and scalable, elegant design such that everything is totally interoperable once and for all. And this means that, I mean, this is a slide from a soon to be coming out explainer video, so hopefully even without it animated, you can get some sense of what's going on, but basically you can imagine there's loads of papers coming out on the archive kind of conveyor belt. There's loads of models and libraries and tools all here. You can't kind of quickly bring them over and try them out at the moment, but now with Ivy you can. Everything that's ever been written that's vaguely related to AI in the history of time and ever will be written can instantly be brought into your training pipeline to try things out at the speed of thought. And this is what Ivy enables users to do, and this is all with one line of code. Once you've then taken this and you've got your experiments done and you've been able to get early verification in a prototyping setting, then when it comes to deploying your model, Ivy ensures that all of the hardware, compiler infrastructure, and frameworks are elegantly interconnected so that you have all of the best-in-class tools directly accessible to you. And this then means that you have happy end users where you have very performant end user applications. You can do so much more cheaply and cost effectively because you have all of the best-in-class tools nicely packaged together into one. And with all of this, Ivy is taking steps to unify everything and make it easier for everybody else. Finally, when we talked about these higher level tools that build on top of the stack, Ivy enables them to focus on their tool, not worry about trying to keep up with all of this infrastructure, just focus on what they do best. They can build on top of Ivy's unifying representation, and everybody benefits from this, this simplified landscape. And basically, this is a high level. So I've tried to start with at least give some kind of very high level intuitive images to give you a bit of an idea about what we're doing at Ivy. But now, of course, I'll go into the meat a bit more and dive into some of the details with exactly how Ivy works, how it can be used, and what it can do for you. So first level on Ivy's design. So basically, Ivy enables anybody to run any model, library, or function using any framework on any hardware. So you can take a TensorFlow model, a PyTorch library, a NumPy function, run them together in JAX, and everything just seamlessly works together. In terms of why we're doing this now, as I've outlined earlier, we have a ton of frameworks that have come out. They continue to come out, and developers need to continuously migrate between these and integrate these. It's not only the frameworks, it's also the compiler infrastructure, as I've said, and this is not a good thing for developers who want to move quickly with their development efforts. So to outline the problem a bit more, so whether you're a researcher, a startup, or a large enterprise, you basically need to back a horse with your frame installation. Maybe you choose PyTorch because it's very good for rapid prototyping, it's got an amazing ecosystem, but it's very poor for runtime performance. Maybe you choose JAX or Julia because it's very good for runtime performance, but again, not quite so good when it comes to rapid prototyping. And also doesn't have quite the same ecosystem built around it. Maybe you choose TensorFlow because it's got very good bindings for edge and mobile devices, specifically via TF Lite. But again, it's not got the same, it's not as easy to kind of quickly hack things together as it is in PyTorch. But it has, as I say, lots of benefits when it comes to deploying to edge and mobile devices. So basically, you have all of these different frameworks, they have their own benefits, their own downsides. You need to make a compromise. You need to say, well, we'll take these features because they're good, these features suck and aren't so good. Let's just, find a happy middle ground. With Ivy, you don't need to find any middle ground or make any compromises. And you no longer need to think in this monolithic way when it comes to the frameworks. All of the tools, libraries, and capabilities of all of these frameworks are simultaneously accessible to you instantly, all with just one line of code. So to go a bit more into how this works exactly, so basically we have a functional API in Ivy which unifies all of the, it's a unified representation in terms of syntax and call signature, So for every framework, the function looks and behaves exactly the same. We then populate this unified function with framework-specific backends under the hood, and then we basically recreate the behavior of the frameworks, building these mimicked APIs as a composition of our unified Ivy API. And the way that this then enables us to convert code between frameworks, for example, if you want to add TensorFlow code to a PyTorch project, it is as simple as using the TensorFlow front end with the PyTorch backend, and it's as simple as that. So we just go straight through. The fact that we go through our intermediate representation means that we don't need to create a unique front end for each framework, uniquely for every backend. We just have a linear scaling, so whenever we support a new framework in the future, we add one front end, one back end, and then it suddenly works in this kind of switchboard analogy. So that's the framework itself, and the functional API specifically. But Ivy is not just a transpiler, it's also a fully fledged machine learning framework itself, where we basically have a stateful API containing modules and so on. So you can build your neural networks, you can build your data loader class, you can build your trainer class, etc. All of this can be done in Ivy. And the way we do this is that we go directly through our own functional API, which itself only wraps the functional APIs of the existing frameworks. So we don't wrap the high-level APIs, we see these as reinvented wheels, and we discard these basically. And this gives us much more scalability, because basically the functional APIs of the frameworks are incredibly forward and backwards compatible. They have a lot of stability, and therefore things don't change much over time, which makes it a very good representation to build around. So now going into the building blocks. So we've already seen the what we call the backend API, Ivy API, and the front-end APIs. This can then be represented as these three blocks. So again, the Ivy API is our unifying functional API. We then have a backend handler as well that enables us to kind of switch in one of these to represent and fill in this Ivy function template. So that's the building blocks. We then have we have this other image that represents something similar. So these are each of the backend APIs. This is Ivy's functional API, and then we have Ivy's stateful API, which is the container, the modules, all the high-level classes to compose new things. So this then, as I say, the backend API. This is the Ivy API, and then we have a stateful API, which contains a container class, which is useful for containing weights in a network and things like this, and also data sets. And then our stateful API, which contains all the modules and so on. So we have these next. Then we also have our compiler, which is crucial both for using Ivy as a framework, but also for using Ivy as a transpiler and converting between code. Basically what the compiler does is it takes any code and boils it down to the low-level functions of its constituent functional API, basically, of the existing framework. So if you have PyTorch code and you apply our compiler, what you get out of that is a pure direct acyclic graph representation of the mathematics of that model that's then discarded the high-level classes and modules and so on. And again, so really we have the building blocks, which are shown in orange, which are necessary both for doing code conversions and for using Ivy as a framework. We have the purple, the front end, which is only really used for Ivy as a transpiler. And then finally, we have those in green, which are only useful for using Ivy as a framework. So what we can then go into next is talk a bit about how this fits into the broader ML stack. So at the very top, we have API standards. These are basically, well, the best one is QuantSight, the array API standard. This is basically a template of what the functional API should look like if it was totally unified. So there's no implementation here, it's just saying this is what the functional API of a machine learning framework should look like in a standardized way. We then have framework wrappers, where they have tried to enable users to create new machine learning applications which are can be run with any backend. So when you build something with Think or EagerPy, you don't need to lock yourself into PyTorch or TensorFlow. You can use any of these in the backend. And obviously there's very similar flavors with what we're doing with Ivy. And we kind of see ourselves as being a bit of both because we adhere to the accepted standard and we also enable a switchable backend when writing Ivy code. Where we go one step further is then enabling conversion between the frameworks as well as other features as well. So then we have the frameworks under the hood. So these are the actual frameworks themselves, which are of course not interoperable. They are fragmented, which is why we've got this red box around them. So all kinds of frameworks for all kinds of different things. We then have graph traces, which the frameworks use under the hood to extract graph representations. So this is really fragmented again. We see kind of some unifying efforts, deeply fragmented layers under the hood. And then we come back to some other unifying initiatives, such as neural network exchange formats like ONNX, NNEF, CoreML, for example. These are just unified file representations that some consensus has been emerged on to then actually represent these ready before we then send them off to hardware for deployment. We then have compiler infrastructure, where this is, again, trying to unify things through the lens of hardware fragmentation. There's all these different hardware vendors. How can we come up with repeatable standards for how to write compilers and representations that transcend specific hardware vendors? So again, some good, helpful unifying efforts there. Multi-vendor compiler frameworks as well. You could link this into compiler infrastructure a little bit. There's kind of a hazy line here for things like XLA, GCC, TVM, etc. And then we get, again, fragmented. We have vendor-specific APIs like CUDA and TensorRT. We have obviously kind of Intel compilers and so on. So then you get assembly languages, compilers and so on that are fragmented across all these different hardware vendors. So we have this kind of like some effort to unify things, not so much, a little bit again, not so much. So this kind of deep stack where there's hints of unification at some points, but none of them have really made their lives easier. And in many cases actually, because these are, you end up with lots of competing standards, even in the places where there's unification efforts, it still doesn't mean there's a one-shoe-fits-all, really easy for the end user approach to unify all these things together. And this is really where Ivy's coming in to try to make a difference. So what does Ivy add? So as I was saying, when you try to unify things by creating a new standard and saying, hey guys, this is now the standard, best case scenario, some people adopt it, but unfortunately many still won't. And we then, of course, can't expect every third party involved in the whole of ML to suddenly come to you and work on their integrations with your standard. And then we end up with things like this, where with this XKCD, we see another standard arrives, and then the problem can often get worse. And there's some truth to this, where lots of competing unifying standards is even worse than having none of them to some extent. And there's lots of initiatives that are working to make things better and unify things, but I think without proactive focus on integration and cross integration, then we do have this problem a little bit. So how do we deal with this? So we're taking a proactive approach to implement bindings to everything else. We don't need consensus. We don't say to anybody, hey, this is the standard, now you guys come to us. We're like, no, we will proactively integrate with everything that's out there and make sure that it works really, really well from our repository and from our development standpoint. Ivy's totally complementary. Nobody needs to jump ship at all. It's not like we're building a new unifying framework and everybody needs to start using it. We're saying, you have your code in your version of your framework, whatever it is, we'll make sure that you get all of this benefit with one line of code. And that's all you need, regardless of what your machine learning looks like today. So this is another thing that makes us stand out. And also it's based on the accepted array API standard. So this is from Quantsite, a consortium for array APIs, and with the backing of PyTorch and TensorFlow and Google and so on, this is what the field has coalesced around as being the best standardized representation for the computing mathematics with arrays, and we are adopting that entirely, and we're the only framework that adopts that as well. Okay, so now what we can do is go through a few examples. So I've given a somewhat high-level view of how this works, but actually now let's dive into the code and see for ourselves exactly what this looks like. Okay, so now let's dive into some of the demos. So first of all, we're just going to install a lot of the dependencies. I've actually done that ahead of time, so save your time. Let's import Ivy, and let's really, to start with, focus on Ivy as a framework. So again, just to reiterate, Ivy can be used as any kind of drop-in replacement for PyTorch or TensorFlow or anything like this. It really behaves as a framework in and of itself. First of all, we have the backend handler where you can set the backend framework. So when using Ivy as a framework, Ivy wraps the functional APIs of other frameworks under its hood. So you set the backend, it can be JAX, it can be TensorFlow. In this case, it's TensorFlow, set backend, pass it as a string, and now when we call Ivy, it's going to be running TensorFlow under the hood. Okay, so now let's look at some of the data structures. So like any framework, we have an array class for storing multi-dimensional numeric values. But with Ivy, our Ivy array class wraps the array class of the native framework. So under the hood, if we, for example, have set PyTorch as the backend, basically what we see is that the Ivy array class is an Ivy array, but the native array, which is this Ivy.native array, and this is this then returns the torch tensor directly. So we can either kind of have the high-level wrapped array, or we can provide the native array directly, and an alias for this is just ivy.native array, which will bind directly to the array of the underlying framework. So now just to show some very super simple examples of using the framework. So we can set the backend, to whatever we want. In this case, let's say we set the backend to JAX. And then we do a map mul and we return the output. In this case, let's do to native, and we'll see that what we get in each case. So we do a first example with JAX, we do another example with TensorFlow, we do another example with Torch. In each case, what we get are arrays for different frameworks. And this shows that under the hood, under everything that's going on at Ivy, it's just the original framework doing the heavy lifting and the computation, and we've created this unified layer for orchestrating the functions in a unified way with unified syntax and call signature, etc. So then what we can also do, you can also pass in the native arrays directly themselves. If we turn array mode off, for example, and in this case, you can create native arrays, you can pass them into the functions in mapmul in this case, and then the output itself will directly be the Ivy array, basically, as you can see here. Okay, so then what we can do, importantly, is we can then compose new functions using Ivy. So we can, create a sigmoid function, for example, if we want to. Of course, in reality, this has got its own function anyway, but just for the purpose of example, we create a new Ivy function like so, and then this new function can be used with any framework very easily. So this function will now accept arrays from TensorFlow, JAX, or PyTorch, and it will compute the value that you care about with any of these frameworks very easily. So that's the functional API with some really simple examples. Now going into the stateful API. As we saw in the slides previously, the stateful API builds on the functional API, but also provides the container as well as high-level classes, such as the Ivy module, which we'll show now. So let's say you want to build your new network, and you want to build this network in Ivy. All you need to do is subclass the Ivy module, and then you define your neural network layers, linear, for example. You then define the forward pass by overriding this abstract forward method, and then you have your network, as simple as that. Very similar to how you might build a model using Keras or Torch modules, really the same kind of thing. But now, the difference being that your model is now ready to be used in any training pipeline with any framework at all. And so let's create this. So we've defined this regressor class. And then what we can do is set the backend to Torch. We can then define the number of input dimensions, the number of output dimensions, and so on, define the optimizer, and then we can train this model as well. So let's say we want to train with 2,000 examples on a simple regression problem expressed like this, just a very kind of simple curve fitting problem. And then we define the loss function, we do training for epochs. We take this fully functional approach where we do execute with gradients, and then we pass the function with which we want to compute the gradient with respect to, pass the variables of the model, and then we can just do our optimizer step, taking a fully functional approach, not too dissimilar to JAX. And then at the end, we'll see that the training loss goes down, and we're able to fit the model. And this is a toy example, again, just for the purpose of demonstration, but you can train large language models, you can train large computer vision models and so on using this approach, and do so without any loss in accuracy, runtime, or anything at all. And you do so in a way where your entire training pipeline is framework agnostic, and if it turns out that for a particular model, it will be quicker to do it in JAX on a TPU, then it's as simple as changing one line of code to ivy.setback in JAX, basically. So this is how Ivy as a framework can unshackle you from the bounds of your particular framework, and you're now developing this higher level, purely mathematical ether without being limited to the particular framework of choice. So now a few points on the graph compiler. So as we mentioned earlier, the graph compiler enables you to take any code and decompose it into its constituent functional building blocks of the underlying framework. So let's say we have a simple normalized function written in Ivy, and then we go to compile this Ivy normalized function, and we want to compile it to Torch, let's say. We can then do so. So we import Torch, we get a Torch tensor, we have this normalized function, we want to compile it to Torch. What we then get is a graph as follows, which basically shows that we remove the wrapping. What we have here are Torch functions themselves, so torch.std, torch.mean, torch.div, etc. These are not Ivy functions, and these are also Torch tensors. So we've removed kind of all of the wrapping logic, and we now have a graph which is purely PyTorch tensors and PyTorch functions under the hood. So we always remove the wrapping to expose a directed acyclic graph representation of the function, basically. And what you'll then see is that, of course, when we compile, the compiled version will run more quickly because it's just bare bones code, whereas the non-compiled one will run more slowly because it includes this Ivy wrapping code as well. So you'll see that this is it's 1.21 milliseconds in this case, and this one is 15 microseconds, so much faster. And of course, this is a toy example. It's a simple normalized function, but for more complex models, again, we see the same kind of speed ups, in so much as removing the wrapping code from Ivy. And then we can also set the return backend compiled function to true, which will also apply the native framework compilation logic. So it's not just unwrapping Ivy logic, it's actually using the framework specific compiler to go down to machine code in C++ to make things even faster. And again, we'll see that this improves the runtime even further, and we half it, well, more than half it again, now going to 21 microseconds instead of 50 microseconds. So huge speed up by doing our compilation logic and with return back and compile function set to true. So this is how we can write Ivy code, this is how we can make that code run quickly and efficiently. Now what we can do is go through a little bit about how basically the compilation process can happen eagerly or it can happen lazily. So if we want it to happen eagerly and we want to get the compiled function immediately, basically we call the function, compile, and we pass the arguments in, and the function tracing will happen immediately, and we'll get the graph directly. Eager graph is already compiled, ready to be called. However, we don't need to provide the arguments at compile time. We can provide the arguments at runtime, and then it will happen lazily. So in this case, the graph is not yet initialized, it's not yet compiled. We've just primed it to be compiled on the first run of the function. Then we call lazy graph, and this is when the compilation happens. And this will be quite slow because it's still doing the compilation, but once the compilation has actually been done under the hood, then it will be quick because it's been executed after the function tracing from the argument in the prior call. So quite flexible in terms of when you want to do the compiling. Do you know the arguments at compile time, or do you want to wait until runtime and do the compilation lazily, basically? So this is kind of Ivy as a framework, Ivy as Ivy's compiler, but now I think where the biggest benefits arrive quickly is when we start to think about Ivy as a transpiler. So we've just learned how to write framework agnostic code and how to compile this into an efficient graph. However, many code bases, libraries, and models have been developed and will continue to be developed using other frameworks, of course. And really, if you want to be able to take any of this from there, bring it into your project, and so that everything works together easily, this is where the transpiler comes in. And I'll show this with a few examples. So first of all, let's say that you have some torch function. Again, this is a super simple function, but it could be a complex PyTorch library like PyTorch Geometric or Cornea, or many of the Hugging Face models and so on. But in this case, it's a simple PyTorch function, and now we just want to turn it into a JAX function. Well, with one line of code, we can now turn this normalized function directly into a JAX function, such that it will work in any JAX project or any JAX training pipeline. Similar to compile, the transpile function can be used eagerly or lazily. In this particular example, it's being done lazily, where we actually do we call the normalize, so we create the function here, and then actually when we call JAX normalize with the inputs the first time, that's when it actually all occurs, and then we do the transpilation from PyTorch to JAX on the first invocation of the function, basically. And then what we'll get is that this JAX normalize, it works. It's now a working JAX function, even though the function was written in PyTorch originally. So that seems okay, but actually if you had to convert every function independently, that would be not very helpful and it would be a nightmare. So Ivy also enables the transpilation of entire libraries. So let's take Cornea in this example. So let's import it all and then show that we can take this whole library, which is hundreds of PyTorch functions, and with one line of code, we have them all primed to be used in a JAX project, for example. So with one line of code, we take Cornea, source is PyTorch in this case, to JAX, and it's done. And it's done lazily. So again, we don't want to pass every conceivable argument of every function during this function call. So it's much better, particularly when transpiling libraries, to do things lazily. And then let's just do a simple example where we get an image, we open the image, and we're going to basically then call the image first. So let's just kind of take a look. And this is, of course, JAX. So we're showing the image, which itself is a JAX array. And then what we can do is we've now got this new JAX-enabled Cornea, which doesn't exist without Ivy. Cornea is a PyTorch library, but now we've made it work with JAX just with one line of code. So let's now try it out. Let's enhance the sharpness of this JAX image and see what we get. And you will see at some point when the internet bandwidth decides it's time to work. Well, first of all, you'll see that the return is a JAX array. So this has worked. We've taken this JAX image and we've been able to sharpen the brightness of it. And then, of course, we can actually display the image in NumPy, and things have worked. And this is something that obviously is a really simple function, again, for the purpose of illustration, but it doesn't limit anywhere. So any model or function or library that's used anywhere out there in the wild, you can convert it now to any other framework instantly, which can make it run more quickly, but it also means you can bring it into your training pipelines in your framework of choice and end-to-end train things, and things just work very seamlessly. Of course, Cornea is most beneficial not when enhancing the sharpness of images, but when training this in an end-to-end manner in a broader training loop. So it's worth noting that every operation in the transpiled function is performed natively in the target framework. Again, that means that gradients can be tracked and it can be trainable in the target framework and so on. Okay, so that we've shown any function, any library. Finally, now we can show how this also works with any model. So for the purpose of demonstration, we can define a very basic CNN block using the sequential API of Keras. So we define this model that simply takes a convolution 2D, flattens it, and then has a dense layer at the end. So 3 simple sequential layers. And then we define some input array, which is just a TensorFlow array of this shape. We then have a torch model. We want to transpile this model, which is a Keras model. We want to transpile it to torch, and we've done so here, again with one line of code. And in this case, we did it eagerly. So we've actually taken the TensorFlow inputs, passed them in the arguments, and now this torch model has fully been converted. And now it should work with torch. So we can first test this. Well, is it an instance of the torch model? It is. And now we can then see by taking torch inputs, we can then call the model with our torch inputs, and we get torch outputs in the back as a return. So again, just demonstrating that we can take any model and in one line of code, convert it to the model instance of another framework. But these are all toy examples. I think what would be best to end with is a more concrete example of how this can bring big benefits very quickly. So we import TIM, so this is a collection of models. We then take the MLP encoder. Specifically, we take kind of the mixer model, and then what we want to do is transpile this from Torch, which is where most of the models in TIM are. So we take this Torch model, and this is a big, large model, and we can then transpile this to TensorFlow, like so. Again, the whole thing's been converted. And actually, this is a very good example of how it's not just about transpiling one thing, but actually things become very composable and plug and playable, you could say. So we don't necessarily have to train this model in isolation. It might be the case that we have a broader TensorFlow model, and we'd like to try just a different encoder. We have all this other stuff for our particular problem, but we want to just try lots of different encoders, and a lot of them are in PyTorch, and we can't try them very easily. Well, now that's okay, because we can take this PyTorch encoder, we can transpile it so that it now turns into a TensorFlow encoder, and we can then have this TensorFlow encoder as the encoder attribute of our larger, higher level model, which we're doing end-to-end training on our dataset with our data loader, etc. So again, an example here of how transpiling is making things composable, particularly when it comes to training on your own data and fine-tuning on your own data. And then what we get, of course, we have this high-level classifier, which you will see consumes TensorFlow inputs, and we get a TensorFlow output as well, of course, on the return. Okay, so that's how the transpiler enables speed of thought prototyping, particularly when it comes to training. So as the final example now, we can show how this can bring runtime speedups. So we've shown how it enables you to be more flexible when it comes to training. But now as the encoder consists of TensorFlow functions, so the final example is showing how we can take a model, a PyTorch model, convert it to JAX, and then get big runtime speedups. So first we load the model. We import JAX, of course, first of all. We load the model in, we get the model here in this model variable. We can download a sample image from the Koga dataset, and then we can transpile the model to Haiku. So Haiku is the high-level wrap here around JAX, so very high performance. And then what we can do is basically take our feature extractor. So here we go. So get the feature extractor first. We call that, and then we can see if there's an improvement in runtime efficiency. And when we run the compilation, we'll see that by converting to JAX, we do have an increase in runtime performance, particularly when we call jax.jit under the hood. So let's, just until this cell is loading, I'll load this one, and then we'll see the runtime speed up. And we get, just by converting this model to JAX, we get a 2x speed up for free. And this is really just the tip of the iceberg when it comes to what Ivy can do in terms of deployment. So if just by converting this model from PyTorch to JAX for free, we get a 2x speed up, there's a whole ocean of untapped optimization potential that we're only at the tip of the iceberg for when it comes to other compiler infrastructure that we can plug into to get even bigger speedups, particularly when taking PyTorch models. But of course, in this simple case, it's not quite 2 on this particular instance, but going from 7 milliseconds to 4 milliseconds, and all it took was 1 line of code is is quite a powerful tool, and this isn't overfitted for this model at all. You can do this for any model on the entire Hugging Face repository, and you'll get the same kind of results. So this is what I think will become a big use case of Ivy, which is going to be improving runtime speed, basically. And obviously what we can then do as a final sanity check is make sure that the results are the same for both models, and that actually the model isn't just fast but totally wrong, and they are. You see that when we run this all close, you can see that in both cases within each of the -4, they are the same results. So without any change in what the model is doing, and with very, very minimal differences in terms of output, we get a huge runtime speed up, and I think that's really just the very tip of the iceberg, really. So now quickly then going back, just to wrap up. So we've gone through the code. The very last point I'll leave everyone with is just a bit about the team, as well as our roles and so on. So our team is really spread all over the world. We have people working in 18 different countries, so a fully international effort. We continue to bring great engineers on board all the time, so we have internships, full-time roles, etc., that I would encourage everybody or anybody who's interested in getting involved in trying to unify AI, I would encourage people to apply. You can find more of everything by going to unify.ai, and if you scroll down, you'll find careers at the bottom, and you can find all our links for applying. Finally, I would say everyone is welcome and encouraged to join the community. Actually, I made this slide a week or two ago. We now have, I think, nearly 13,000 members on Discord. So a very fast-growing community. So anyone, feel free to snap the barcode and join our Discord community and get involved in all the conversations going on. But for now, thank you very much for listening, and looking forward to seeing you at another event before too long. Thank you.